Hello, everybody, and welcome to now I think this is your 21st lecture in Earth history, geologic history. So this is Dr. Hurt, and we're going to be moving right along to the Mesozoic now. So it's kind of exciting. As you can see here, this is the time of the dinosaurs. Of course, we're not going to be talking about dinosaurs just yet because we're going to be actually focusing today. Like I said, we kind of break this class up into, we look at the geology first, then we look at the life history. So I know everyone's probably excited to talk about dinosaurs, but we have to go over, how and where and when the dinosaurs were living. So we have to understand their world a little bit better. And to do that, we're going to look at the geology. We're going to look a lot at Pangea today and the breakup of Pangea. So that's kind of the major theme that's going to be going on throughout this lecture. And you can notice I even have this little GIF here in the bottom left-hand corner that's kind of showing the breakup of Pangea and the creation of our modern day world, right? So anyway, that's what we're going to be talking about today. Now remember, just to kind of go back to our geologic timeline, we are in the Phanerozoic Eon, we are in the Mesozoic era now, and we are going to be talking about these three famous periods. Probably a lot of you recognize some of these names, Triassic, Jurassic, Cretaceous. Those are the periods of the Mesozoic era. You, of course, don't need to know any epochs and worry about epochs yet, but you do need to know that the Mesozoic went from 252 million years ago to 66 million years ago. So those are dates you definitely want to know for the test. So anyway, that is kind of the time period we're looking at. Remember, now we have just left the Paleozoic, we've left the Permian, and we're going to be getting into the Triassic, Jurassic, and Cretaceous. So kind of the way that this is structured is first we're going to look at big global changes that were going on in terms of plate tectonics. And then we're going to look at Laurentia, Laurasia. Of course, we used to call it Laurentia or Laurasia back in the Paleozoic. Now we're going to call it North America. And we're going to look at development of North America more closely and end there, okay? So that's kind of the game plan for today. Now, at the start of the Mesozoic, right, so we're talking about early Triassic, 237 million years ago. This is what things looked like. So Pangea was intact. Okay, so remember that Pangea was kind of coming together at the end of the Carboniferous through the Permian. But these supercontinents you see don't really last very long. So it doesn't take very long until Pangea is going to start rifting apart. So just to kind of like take you through some big parts of Pangea. In the Pangean world, the Triassic world, remember we have the Panthalastic Ocean. That's been a major ocean all through the Paleozoic, continuing into the Triassic. We have the old Tethys Sea, which is pretty small now, it's been opening up. I'm sorry, we have the old Paleotethys Sea, which has been closing, and the Tethys Sea, which is opening up. So you can see that the Paleotethys is surrounded by all of these subduction zones. So it's going to be consumed pretty soon, because remember, subduction zones are where ocean floor is destroyed, okay? And you can see that the Tethys is going to be slowly opening up more. So the Triassic is a relatively cool time. Pangea is still clustered together. The mountains have been created. There's a lot of highlands, right? There's a lot of just mountains from the assemblage of Pangea, because when you have continents collide, they build up mountains, and those they thicken the crust. All the sediments that pour off of those mountains and the erosion of those mountains builds up the crust around it. So the highlands and the mountains are getting larger. The paleo-equator at this time was kind of right, Pangea was kind of sitting right on the center of the equator. And we have a lot of rain shadow deserts in the continental interior. So even though it's relatively cool at this time, it's very dry in the interior of the continent. And that's how we get a lot of red beds. These are like, you kind of think of them as sand dune type beds, things that are indicative of desert environments. And evaporites. Okay, evaporites, how water evaporates in hot, dry conditions. So these are types of beds that form basically like rock salt and gypsum, things that have been evaporated out of seawater. So we get a lot of dry conditions that create these things in the Triassic. So I talked about this, I think 2 lectures ago, but just kind of go over it again. You might remember that at this time, Pangea was totally surrounded by subduction zones, and it was therefore totally surrounded by volcanic arc mountains, right? So, you can think of the Andes Mountains today. Those are volcanic arc type mountains. So warm, moist air comes in from the Panthalastic Sea. As it rises up over the mountains, it cools, it condenses, and you get rain. You get rain on the kind of windward side of the mountains. On the continental interior, however, this air has been it's totally lost all of its moisture, right? Because it dumped out all of its rain. Okay, it dumped all of its rain out. You can see all the moisture pouring out, and so when it gets to the other side of the mountain, it's dry. It's bone dry. So as it descends, it heats up again, and you get these kind of hot, dry conditions on the other side of the mountain. So the continental interior. So this side of the mountains would have been, the continental interior is going to be hot and dry. So you can see that when we kind of like draw these different artist depictions of what probably the world looked like at this time, you can see that large parts of the Triassic landscape looked kind of like desert, right? So that's kind of how they're drawn, look like desert, arid regions. So you have this situation where the interior of Pangaea is surrounded by many mountain chains, and these mountain chains cause the rain shadow effects that lead to high evaporation, hot, dry conditions on the interior. So that's where you get all these red beds being deposited. So you have all these desert deposits that show that the interior of Pangaea was arid in many places. The Navajo sandstone, so a real famous geologic formation, Arizona. It's a Triassic, Jurassic sandstone, and these very interesting kind of forms you see in the sandstone. You'll see these kind of weird lamentations, these weird shapes. Those are actually preserved sandstones. We call that shape, that kind of very characteristic. Kind of, I don't know exactly what the term, what the right word for it is, but all these little kind of cross lamentations, we call that cross bedding. Okay, and cross bedding is an indication of preserved sand dunes. So it's an indication that these were desert environments. Okay, so this Navajo sandstone, currently in Arizona, Triassic, Jurassic age, showed that we had a windswept, what's called an aeolian environment, a desert, windy desert environment. Okay. So we also had a lot of evaporites accumulating here. So when Pangaea starts to break apart in the early Mesozoic, you can imagine that we get these very shallow seas just as the rift valleys start to open up. So these shallow seas fill up with water, but the interior of the continents here is still hot and dry. And so we get a lot of evaporation from these little shallow seas on the interior, and you get evaporation of those things, and you form these salt domes. Okay, so and salt deposits. So notice in the early Atlantic basin, water flow was highly restricted, right? So you can see how restricted water flow was around here. Okay, there's only these little openings that allow the Tethys Sea to flow in and open up. So it was very highly restricted water flow. So it was very easy for these basins to fill up with water and then just evaporate away because you just have this restricted water flow. So you get these hypersaline inner oceans, and you deposit all of this rock salt. So we have a lot of this rock salt, deposits to this day, even in the Gulf of Mexico. It's actually very important to the formation of some of the oil deposits that we have in the Gulf of Mexico in this day. So higher latitudes were temperate and were humid, and that allowed for, because usually when you're at higher latitudes, things are a little bit cooler, right? So we're a little bit away from the equator here, and we get situations that are kind of more humid and more like forests, and we get a lot of swamps, and those always are more, I guess you can say, conducive to coal formation, things like that. So at the start of the Jurassic, the Gulf of Mexico starts to open up. So now we're starting to get in the Jurassic rifting apart of Pangaea, and we're going to start to make the new kind of orientation, current orientation of the continents. Okay, so Pangaea starts to rift apart. You can see right here. So North America starts to split off from Gondwana, and at this time, South America and Africa were together, as well as Antarctica and Australia. So we refer to this largely as Gondwana. Okay, but we're going to see this rifting between North America, Africa, and South America. And then we're going to see rifting in the Jurassic between Africa and Antarctica. Okay. And now we're also going to see this kind of rotation. You see how there's a subduction zone right here? So this Paleotethys C is going to get swallowed up here at the subduction zone. You're going to see this rotation, kind of like clockwise rotation of Europe, China, and Siberia. Kind of you get this rotation downward. Okay, so I hope you can all kind of make sense of that. So here you go, late Jurassic. Things are opening up here. Gondwana's rifting apart from Antarctica, or South America and Africa are rifting apart from Antarctica. So you have the rifting of Gondwana. You have the rifting separating North America from Africa and South America. Okay, so this is going to be now the new Atlantic Ocean, which is pretty cool, right? And you have the opening up of the Gulf of Mexico as well. So it's pretty cool. These are current, finally we're talking about oceans that we recognize today, right? No more of this Tethys and Paleotethys and things like that. So you can see now the Paleotethys is totally gone. There's actually, I don't think any traces of it left, but we have now this Tethys Ocean. So the Paleotethys is gone, but the Tethys is going to start. You'll notice that we have a new subduction zone right here, and now the Tethys is going to start slowly getting swallowed up at that subduction zone. And you can see again, we have this continuing clockwise rotation of China and Siberia and the rest of Eurasia, swinging down and swallowing up the Tethys Sea. Okay. So at this time, again, we have this very restricted flow of ocean water early in the Triassic. Okay. So you can see that we're kind of stopped. The ocean currents are stopped from flowing in the interior of the early Triassic continent. Okay, the Pangaea. So this kind of led to, again, more evaporative, hotter, drier conditions. Okay. Now, as things start to open up, okay, so we get a little bit of rifting of the Gondwanan landmass. You can see that water flows a little bit better. So now we can actually get some circulation of the oceans through the continents. That's going to help to kind of cool things down a little bit and kind of change, pretty drastic changes to the climate. Okay, so by the late Cretaceous now, we have, only 94 million years ago, you can see that things are starting to look a little bit kind of what we're used to. Okay, so you can see North America here has split off. You have the opening of the Atlantic Ocean. You have the opening of the South Atlantic now as South America and Africa actually start to rift apart. Okay, I should probably put this in red so you can see it a little better. So South America and Africa are rifting apart in the Cretaceous. It's opening up the South Atlantic Ocean. You can see that the Tethys is getting smaller and smaller as we continue this subduction zone. It's swallowing up the Tethys. Okay. You can also see that India and Madagascar have basically split off here. And India is going to start this northward march and continue, which it's still continuing, and collide eventually with Southeast Asia. Okay. You can see now that even Antarctica and Australia are starting to rift apart. So there's just rifting happening during this period, during the Cretaceous. So very drastic changes are taking place. So here you go. This is the Triassic. There's Pangaea. Into the Jurassic, okay, we see the North Atlantic opening up here, rifting. We see India, Antarctica, and Australia rifting apart from the larger Gondwanan landmass. By the Cretaceous, you can see things are kind of looking a little bit more similar to what we're used to. Okay, we still have to have Australia and Antarctica separate and go their separate ways, and we still have to have Europe disconnect from North America entirely, but that'll happen in time, and that's what it looks like today, right? Okay, so just looking at this, just like a little quiz for you. what era, or I'm sorry, this shouldn't say era. Whoops, what a mistake. What period of the Mesozoic do you think this is? So hopefully you can look at this and you can be like, that's the Triassic, right? So because Pangea is mostly put together here, right? And you see the Paleotethys Sea here. You see the Tethys. Okay, and this is the Panthalastic Ocean over here. And you can see that Pangea, though, is mostly all put together, okay? So that's kind of what happened during, just globally during the Mesozoic, okay? And you can see that mostly it's just a story of rifting, okay? Rifting a part of Pangea. So I'm going to show you just a little Christopher Scotty's video. Again, he's this brilliant paleomagnetism scientist. I just want to show you his video, kind of showing us what happened in the Mesozoic, okay? So hopefully you should be able to look at this video and kind of understand what's going on. Okay, so here we go. This is 299 million years ago, so this is in the Permian, okay? So I'm going to stop it once we get to the Triassic. Okay, so now we're 250 million, 257, 253. So we're at the Triassic right now. Okay, so here's the Triassic, and you can see the continent is basically all put together. Pangean continent's basically all put together. Okay, so again, here is, you know, the Paleotethys. You can see the Tethys Sea is opening. So this red line that you see right here, that is a mid-ocean ridge. It's a spreading center where we're going to get the opening of the Tethys. And you can see the Paleotethys up here is surrounded by blue subduction zones. So that means it's going to be closing up, okay? And like I said, you can see that the whole Pangean continent is basically surrounded by these subduction zones that creates the mountain building on their on its margins, okay? So, whoops, let's play a little bit forward. So you can see now the Tethys is closing here. The Paleotethys is closing here. The Tethys is opening up. And let's start looking for rifting. Okay, we're going to start looking for rifting, right? So you can see this clockwise rotation of Siberia and Eurasia. Okay. So now we're moving into the Jurassic. And there you go. Now you start to see rifting here. Okay. You start to see rifting right at the end of the Triassic. 150 million years ago is the beginning of the Jurassic. So you start to see this rifting of the North Atlantic here. And you start to see just the very beginnings of rifting here between Africa and Antarctica. Okay. So now you see that rifting is just going like gangbusters. And as we move now we're into the Jurassic. Okay. And now we are just getting into the Cretaceous. Okay, so now we're in the Cretaceous, and you can see everything turns red, right? And the red is the rifting. So we're getting rifting. India splits off. India splits off from Madagascar. Madagascar splits off from Africa. And you can see we have the opening now of the North Atlantic. We have the opening of the South Atlantic. And things are starting to look a little bit more like we're used to. You can see Antarctica now rifting apart from Australia. And this is the end of the Cretaceous, right? 66 million years ago. And you can see that things look very much, much more close to like what we're used to in the world today. So it's definitely still, things are closer together, but you can see that things are looking a little bit more like what we're used to in the modern day orientation of the continents, okay? So that's how it all goes. Now let's focus in on North America during the Mesozoic. So during this time, we had the Appalachian Mountains, and of course they were built up all during the Paleozoic, starting 300, 400 million years ago. We're starting to get the first orogenies that are building up the east coast, all the way up, through Canada, Greenland, Scotland, and then down into our country, right? We start with the Caledonian orogeny, the Acadian, Alleghenian orogenies, and that's part of the larger Appalachian orogenies and Ouachita orogenies, right? So these are all very high mountains now, And I mean, at this time, I mean, the Appalachians were probably like the size, I keep saying this, but they're probably like the size of the Himalayas, right? They were big, big, tall mountains. So these were huge, huge highlands, okay? Huge mountains, lots and lots of sedimentation must have been taking place here as these things get eroded away. So now we're going to start to see in the Triassic, we're going to see some other orogenies taking place now on the west coast. You know, during the Paleozoic, we just had a little mini orogeny there with the antler orogeny. That was the only west coast orogeny. But we're going to start to see more development now of the west coast of our country and the Cordilleran area. So remember that this is like the Appalachian side of things, and the other side over here, the west coast, is the Cordilleran side, okay? So some of the key developments during the Triassic, we had Appalachians are very high, very well developed. We had a worldwide transgression. That means high sea levels. Okay, so we had deep empiric seas covering North America. We had the Sonoma orogeny on the west coast. Okay, and the Sonoma orogeny is resulting from the subduction of the Farallon plate. Okay, and there was the ocean plate at that time was called the Farallon, subducting beneath the west coast, and you start to build up the Sonoma Mountains, which is, again, all part of this larger Cordilleran. This is all part of the Cordilleran mobile belt, okay? So again, you have this dry interior, a lot of red beds, kind of desert-type environment that was laying down sandstones and sand dune type deposits. The west coast is a subduction zone, so you have terrains accreting. Okay, so you have these different terrains that are accreting on and building up our continent. And at this time, we were located at the equator. So we were like a tropical equatorial environment at this time. So you could imagine it's a very, very different sort of climate, very, very different kind of environment that we would have had during the Triassic, right? You're thinking about hot, dry conditions, equatorial, you know, these shallow seas covering a lot of the continent. So that's how things must have looked, right? So you can see that all the way up to like Wyoming and Montana, right? New Mexico, Texas, that was basically all like coastline at the time. So even here in Texas, you know, we would have had like it would have been like the west coast basically, right? Because you can see these shallow seas. And off the coast of the shallow seas, you see these volcanic arcs that are building up, okay? Moving into the Jurassic, we get even more expansive shallow seas covering even larger areas of the United States, or North American continent, I should say. And we call this the Sundance Sea. So we're going to talk about that a little bit more later. But you can see you can see how the Cordilleran is now really building up, and the Rocky Mountains are really starting to build up at this time. And on the flip side, the Appalachians are starting to wane. You know, this is now starting to open up as a rift zone, and subduction has stopped here. So these are just, the Appalachians are going to start to erode away and wane. We have the Sundance Sea, covers the middle of the North American continent, and we have the beginning of what's called the Zuni cratonic sequence. Okay, and of course, cratonic sequences, just to remind you, that's when you have the continents covered by these shallow inland seas, and they lay down these marine rocks. Okay. So this is a portion of the Rocky Mountains. It was built in Montana during the severe orogeny. So severe orogeny was a very important orogenic event that was happening on the west coast. The severe orogeny, along with the Laramide orogeny, which we'll talk about later, were responsible for building up the Rocky Mountains. Okay, so the Cretaceous in North America, we get the Laramide orogeny that continues to build up. Okay, see now going into the Cretaceous, you see how high the mountains are getting now and how well developed the Cordilleran mountain belts are getting. So we have this worldwide transgression, high, again, very high sea levels. You can see that, wow, a lot of North America, you can see in this kind of pale green color. This is all covered with sea, okay? So you can just see that the Canadian Shield and the Appalachian Mountains are really the only things sticking out on the east coast. And of course, the Cordilleran areas are sticking out on the west coast. Okay, everything else is covered with ocean water, including Texas. Okay, so the Cretaceous interior seaway is what we call this interior sea going through here. And we have the continued erosion of the Appalachians. So just kind of look at how things change. So first of all, look at how the Appalachians change going through the Mesozoic. So you can see they're big here, getting smaller, and finally getting smaller in the Cretaceous. That's because they're eroding away. On the flip side, the West Coast is going gangbusters, right? It starts off these little pockets of mountains here. Okay, they get bigger and more developed with the Sonoma and Sevier orogenies and the Laramide orogenies, until the final Cretaceous Laramide orogeny really builds up the West Coast mountains and the Rocky Mountains. Okay, so that's kind of just an overview of what was happening in North America at the time. So at this time, the Paleozoic, the Appalachian Mountains, again, are starting to wane, and they're also starting to rift apart. So as rifting begins with the opening of the North Atlantic, okay, you get all these little rift basins. Remember when we talked about plate tectonics, when we talked about continental rifting, you create a lot of these rift valleys. So there's all these rift valleys that start opening up, and all these little rift valleys, which are still around today, get filled up with sediments from the Appalachians. Okay, so there are all these little normal fault block basins that are laid down. Mostly poorly sorted red sandstones of the Newark group get laid down during this period. Okay, so this is all erosion of, let me see here, erase all this. So you get this whole green area. This is all Appalachian Basin. You lay down all these poorly sorted red sandstones of the Newark group, and you can see all these little kind of orange and red blobs. Those are these fault block basins that are filling up with sediments. Okay, so this is kind of just a depiction of what the East Coast would have been like during the Mesozoic. So again, you're getting this early rifting. So North America is rifting off of Gondwana. It's opening up, and as it opens up, these valleys form, right? We learned this when we talked about plate tectonics, right? This is continental rifting, valleys form. You can look at what's going on right now in East Africa. It's probably pretty similar to what it would have looked like at the time in what is now like New York and New Jersey, right, and Pennsylvania. You're getting this rifting apart of the Appalachians. You're getting rift valleys forming that are filling up with ocean water, okay? And so as the crust gets pulled apart, you see the crust getting pulled apart here. It's opening up all these valleys that fill up with sediments, okay? So along with sedimentation, I think I've explained before might remember way back in the plate tectonics lecture that along with continental rifting, you always get a lot of volcanism. So a lot of basalt volcanism from decompressional melting is forming at this time. So you get all these dikes, all these sills getting in place. Heavy volcanism, heavy basalt volcanism. These big, you could imagine like just oceans and rivers of basalt being generated at this time. Some of the most famous of these are the Hudson Palisades. So again, New York City would have been the epicenter of rifting during the end of the Triassic, early Jurassic. So you get the Hudson River Valley opening up. This is all these really steep cliffs that you see here are the Hudson Palisades. So if you ever go to New York City, you can actually see this. This is along the Hudson River. You get these high, like 90, it's kind of crazy, but 90 meter thick, right? Hundreds of feet thick Mesozoic like oceans, deep oceans of basalt that get erupted. So all this stuff, imagine, put yourself back at this time. This all would have been a deep pool of basalt, and you can see how deep it is. Look at that. This is a little playground right here. You can see how huge these Palisades are, right? You can see the apartment complexes on top. They dwarf these huge apartment complexes. So these were deep, 200 million years ago during the Triassic, very deep pools of basalt that were emplaced as New York rifted apart, North America rifted off of Gondwana. Talking a little bit now about the Gulf Coast, because we live on the Gulf. what was going on in the Gulf Coast. So the Gulf Coast at this time was totally covered with a shallow sea for almost the entire Mesozoic. So this whole area is just covered with Mesozoic aged sedimentary marine rocks. Okay, so because we were underwater basically. So in the early periods, the restricted basin was again perfect for evaporite deposition for sea salt. So again, you have this very restricted water flow within the Gulf of Mexico at the time, within the North Atlantic for that matter at the time. So again, because of the hot, dry conditions, very favorable for evaporation. So we get these very thick salt deposits at this time. So as the seaway opened up, this area became a barrier reef here in the Gulf of Mexico. It was very good for oil formation. So oil formation was a very big deal. We see here, let me get rid of this. This is, it's kind of funny. This is like old writing I left on here. Sorry about that. So this is how Gulf Coast oil, very typical Gulf Coast oil formation. So we have a lot of salt, we have a lot of shales, we have a lot of sandstones, more shale. Okay, so this is really perfect. The conditions back then were perfect for creating oil deposits that we use to this day. And as you know, oil is a big deal here in Corpus Christi. So a big deal in the Gulf Coast. So we have these, this is basically what happens. You have very oil-rich marine shales. Okay, so they're rich in organic matter. They generate the oil. So that is called the source rock. Okay, so that's the rock that actually gives us the organic matter that creates the oil. Above that, you have sandstones, which are very porous and permeable. So all this oil is able to rise up out of the oil-rich shales and into the sandstone, the very porous sandstone. And at the same time, on top of it, now, so this is called, by the way, reservoir rock. The reservoir rock, because it holds the oil. At the same time, you have this impermeable shale. Shale's yet again another very common marine stone that traps the oil. And at the same time, you have these beautiful things happen. You got these salt domes. The salt domes swell up and rise, and they create these perfect little traps for oil. So what they do is they drill down to the sides of these salt domes, and they're able to tap those oil reserves. Okay, so that's how we get oil reserves in the Gulf of Mexico. Okay, so groundwater plays a big role here, because as groundwater flows through the oil shale, it pushes that oil up, because remember, oil floats on water. So that's just kind of a little simplistic explanation of how we get oil deposits, especially more specifically, how we get oil deposits in the Gulf Coast, which is something you should know because it's a big deal here. The West Coast in the Mesozoic. Let's turn and take a look now at the West Coast. So this is the Cordilleran side. We're creating the Cordilleran mountain belts. So we had a lot of Mesozoic orogenies occurring in the Cordilleran. Again, I have all this ink. Gosh, I forgot to delete all this ink on the slides from last time I taught this. Sorry, let me delete this stuff really quick. I thought I got it all, but I didn't. Okay, let me get this. Okay, excuse me, sorry. It's just an oversight on my part. Okay. Did I get it all? Maybe I got it all. Okay. I think I got it all. Sorry for the interruption. Okay, so this is a list of the different orogenies we were getting on the West Coast at the time. So right at the Permian and Triassic, we get the Sonoma orogeny. The Sonoma orogeny was the accretion of a volcanic arc onto the West Coast. Okay, so it's that very common common event of accretion happened a lot during the Archean. I hope you kind of remember what I was talking about with accretion. That's how continents get built up. Later, we get what are called three orogenies that are kind of overlapping: the Nevadan, Severe, and Laramide. And that starts to occur in the Jurassic, okay, and goes all through the Cretaceous. So the western margin during these different orogenies, okay, North America was drifting west as we opened up the Atlantic. The Farallon plate was subducting. That's going to build up. It's going to build up, create a lot of volcanism here on the west coast. It also emplaces the all-important Sierra Nevada batholiths. We're going to talk about those later. We get accretion during the Sonoma orogenies. We get accretion of these different volcanic arcs, okay, and that creates the Sonoma Mountains in the early Triassic. So this is a little diagram showing. Oh, again, I forgot to get ink off this thing. Boom, there we go. So this is a little diagram showing what the west coast would have looked like during the Severe orogeny. So we're getting again accretion of these foreign volcanic belts, these other volcanic belts, volcanic arc belts onto the west coast. It's creating a lot of mountain building. We're getting a lot of melting and metamorphism that comes with subduction, okay? So that's going to emplace the Sierra Nevada batholith into the continent. So the Sierra Nevadas, as we know them now, they are a huge batholith of granite, okay? Very regionally sized, massive batholith. And I hope you remember that batholiths are these plutonic igneous rocks, right? So that was going on due to mountain building and subduction on the west coast during the end of the Jurassic, or in the middle of the Jurassic, actually. So these beautiful granite mountains you see here, the Sierra Nevadas, these were all in place during the Severe orogeny, okay? Again, the Severe orogeny is going on with the subduction of the Farallon plate. So it's all granite, all of it's plutonic granite rocks. And you can see how huge it is, right? This is a huge hunk, like a huge magma body that must have been underneath at the time, and is now amazingly exposed at the surface. So all those surface sedimentary rocks were stripped off, and now we have exposure of this batholith at the surface, okay? So there's another picture of the Sierra Nevada batholith. During this time, we also had emplacement of the Idaho batholith as well. The Jurassic Age, I do want to kind of touch on the Franciscan complex. The Franciscan complex you can find in California to this day, and it represents basically all of these continental shelf, deep sea sediments that got scraped off of the top of the Farallon plate as it subducted. So it creates this melange. It's this mixture of very dirty mixture of different marine sediments, everything from near coast sandstones, shales, marine carbonate rocks, and it all got kind of mixed and mashed and smushed into the west coast of California. It's a very important rock formation in California, the Franciscan complex. It all got smushed in there during subduction of the Farallon plate during the Jurassic. So it's a very rich group of rocks covering everything from deep marine environments. Basically, they were scraped off of the bottom of the subducting ocean wedge, and it actually represents accretionary wedge deposits. So this shows all these folded chert beds, all these mangled, like folded sediments. Because you can imagine at this time, not only was this stuff getting scraped off, but it was getting smushed as the Farallon plate was descending and smashing into the west coast of our North American continent. Okay. So that was the Severe orogeny, right? So you had the Franciscan complex, you have the Sierra Nevada batholith, okay, you have this mountain building going on. It's starting to build up the Rocky Mountains. And after that, you start to get the Laramide orogeny. So the Laramide orogeny begins in the Cretaceous. It's caused, again, by the continued subduction of the Farallon plate, and it creates kind of finishes creating the Rocky Mountains, okay? So the Rocky Mountains don't actually end. Subduction doesn't stop until the middle of the Miocene in the Cenozoic, okay? So this is a very long orogeny and very important for building up the Rocky Mountains, okay? So Rocky Mountains start to get built up in the Cretaceous, or even, I guess, before that, because they're being built up by the severe orogeny during the Jurassic as well. So moving on to kind of some important cratonic sequences that were going on here. One of the most important during you might remember cratonic sequences, right? During the Paleozoic, we had the Sauk, the Tippecanoe, the Kaskaskia, and the Absaroka. Now, the real only sequence we have here in the Mesozoic is the Zuni. So, and you can see the Zuni is massive. It covers a lot of, that transgression of the sea really covers a lot of the North American continent at the time. So this creates a lot of very important, the Zuni transgression, the Zuni cratonic sequence, creates a lot of important rock formations we have in this time. So the Chinle Formation, again, it's Triassic in age, contains many fossils of amphibians and reptiles. This contains also the Navajo sandstone, which I showed you before, and it also creates the petrified forests that we have in Arizona. So here's some important outcroppings of the Chinle Formation, New Mexico and Arizona. Again, it would have been a desert environment, and right there's Petrified Forest National Park. So these are petrified trees left over from the Triassic. Okay, there's beautiful Navajo sandstone. Again, you can see these are desert deposits. These are indicative of an Aeolian sand dune type desert. Okay. In the Jurassic, the Sundance Sea covered much of North America. Again, this is a continuation of the Zuni transgression, the Zuni transgressive sequence. That was very important because the Sundance Sea laid down the Morrison Formation. Morrison Formation is a very big deal. It is a complex of sandstones, mudstone, shales, but it contains some of our best fossils in North America of dinosaurs. Okay, so you can see the Morrison Formation has your beautiful dinosaur prints. Lots and lots of dinosaur fossils were produced in the Morrison Formation. You can see it's huge, right? It goes from the Dakotas into Canada, through Wyoming, Colorado, New Mexico, all these different places. You can find dinosaur bones. So again, in the Cretaceous, the interior of North America was once again flooded with the Cretaceous interior seaway. It was well fed with sediments generated by the Cordilleran, so there's a lot of sediments being dumped into the Cretaceous interior seaway, so we get lots of different sedimentary rocks being formed at this time. Along the coastlines of the Cretaceous interior seaway, so the interior seaway is shown here in teal, and you see these green colors represent these coal forests and lowlands. So these would have been covered with forest. It's where you get a lot of important coal deposits that we have this day. So Mesozoic coal deposits here are shown in this red circle. These were all along the Cretaceous interior seaway, these ancient forests that were eventually flooded and created the coal deposits we have now. So the western half of our country was mostly built during the Mesozoic. So the western half of our country is kind of, I could say, newer and younger than the eastern half. So again, we're building things up by accretion of these volcanic arcs. So you can see there's these little volcanic arc islands, and very similar to like what we have in Japan or the Aleutian Islands, and they are accreting together and sticking onto the side of the west coast. Okay, so as subduction continues, these things collide with the side of the west coast, and that gives us all the Sonoma orogenies, right? The Laramide, severe orogenies, et cetera, So that's the whole process of accretion. Okay, so accretion of volcanic arcs onto North America, and that's how we get the buildup of North America during the Mesozoic. So anyway, that's the lecture for today. Hope you enjoyed it, and I will be talking to you next time we get on to dinosaurs and also the advent of mammals, and a lot of important things happened during the Mesozoic. So we'll talk about Mesozoic life next time. Till then, you have a good one.